So number 1 through number 12, which one would you like to see? Somebody pick one. Somebody pick one you think you cannot. Could you do number 7? What is it?
Could you do number 7?
Number 7. Okay, let's look at number 7. Number 7. Oh, you picked that tricky one. Okay. Okay, so now the limit. Okay, number 7. Now number 7 has an extra computation which we didn't talk about, but we can right now. Okay, so example 7. Let's look at this. So this is the problem number 7. This is file 2.4, limit trick 2. Okay, so let's do number 7 now. Okay, so we look at this limit here. So let's see. First of all, we figure out what this is. So now, if you let this x go to infinity, then what is the limit of this guy right here? The limit of x is going to infinity. Then what happens? If you have this, then what is the limit of what? The 6 minus pi x. 6 minus pi x over what? Over 3x. So if you take a limit here, so why don't we before we apply the cosine, I know there's a cosine. I did not forget the cosine here, but now let's look at this. X is approaching what? X approaching infinity, right? What is the limit of 6 minus pi x? 6 minus pi x over 3x as x is approaching infinity. So the first step is let's figure out what's happening to the argument of cosine without the cosine. So what is this? This is actually equal to what? Can you figure out what this is? Oh yeah, this one we have done it so far. The top is a linear function. The bottom is also a linear function. You have seen this before? Yes. So now this is going to be the limit. The limit of what? The limit of 6 times. This is actually 6 over x. 6 over x and then what? 6 over x and then what? Minus pi. And then over 3.
About what?
Not hard to see. Now note that the limit is x is approaching infinity. Always watch this out. Always watch and remember what this guy is.
Yeah, but not
Do
right
not
this second.
assume that this x is always approaching 0. Always be careful.
We're coming back on Monday, right?
Always be very, very careful because you cannot afford to make any mistake. So this here, x approaching infinity. So what did I do here? What I did was, because this one right here, this is a minus infinity over infinity form. It's a minus infinity over infinity form. So let me, how about this? Let me erase this here for now. This is going to be what form? Infinity over infinity. So this is infinity over infinity form. This is again infinity over infinity. The numerator really minus infinity over plus infinity, but then nevertheless it is an infinity over infinity form. So therefore you cannot plug in. So now we have to change something. We have to do this. Multiply both top and the bottom by 1 over x. You know that trick? Multiplying by 1 over x to the top. Then multiplying by 1 over x again. You're multiplying by 1 over x to the top and 1 over x to the bottom. Why? Because top function is linear, the bottom function is also linear. So we get this. And when you do that, we actually get minus pi over 3.
11.
You know, in this case, no need to convert this x approaching infinity to x approaching 0. We get this. So therefore, this is actually equal to cosine. This guy is actually minus pi over 3.
This is the first thing
This was actually much easier than I thought.
We did it.
So in this case, there's no need to change from x approaching infinity to something approaching 0. We don't need that. This is actually this. And actually the game's over. See? The very first thing you do is try to plug it in or take the limit of that part of the expression, not the whole thing. And by the way, the cosine is a continuous function. So can you apply the limit to the argument? Yes, we can. Again, cosine are continuous functions here. So if it's a continuous function, you can actually put the limit into the argument of the cosine, and then you get what? This is what you get. So basically, this right here is actually equal to, if you like, this is actually equal to cosine of the limit of the function. It's actually this right here. X heading to infinity. So this is actually equal to this right here. So we have cosine of something, and you have the limit here. Because cosine is a continuous function, we can actually secant the limit into the cosine, and then basically we get this. And so the first step is to find the limit of what the argument, what we show here. And then when you do the work here, and the work is right here. By the way, here's the rule. When you have any kind of limit, which is an indeterminate form right here, indeterminate form. So let me write this down. This is an indeterminate form. Any kind of indeterminate form, how much work do you have to show? Any kind of indeterminate form, how much work do you have to show? The rule is this. You have to show me work until the limit becomes not an indeterminate form. So now if you look at this guy right here, this expression is equivalent to this expression right here. They are algebraically equivalent. So let me write this down again. In green, this guy right here is algebraically equivalent to this right here.
What did you work out though?
The algebraically equivalent.
It should be there. I didn't move
Yeah,
it.
algebraically equivalent. Now, but
Or maybe it's in the back.
It was always.
the second limit form is not.
No, it was sitting down there by the
This is
book
just
for a while.
negative pi over 3. So this is heading to
Maybe it's in
here.
the bathroom.
And therefore,
I haven't
this
moved it.
limit form over here we got is not an
Specifically
indeterminate
did
form.
not include the
So this
bathroom
is not
because
Oh, I didn't put it in there, but I'm just saying I don't know.
And if you do not get an indeterminate, then that means it's over. So on every kind of limit problem, you have to show me work until it becomes a non-indeterminate form. And then you can show me the answer. So in this case, what is cosine of negative pi over 3? Let me see. Negative pi over 3 is, cosine of negative pi over 3 is half. If you have a unit circle here, again, I don't know exactly how you study your trigonometry, but cosine of a unit circle like this, you know what, I can draw a circle. How about if I draw a real circle? Let me draw a real circle here. Real circle is right here.
Did you take it to the
That
kitchen?
looks much better. And then, what? And then we have this
I didn't move it.
unit circle. Again, I don't know exactly how you study your trigonometry, but drawing unit circle, and then what? Minus pi over 2 is minus 60 degrees is actually right here. So when you draw minus 60 degrees is right here. This is the point on the unit circle is what? Which is has standard angle negative 60 degrees. So this is minus 60 degrees standard angle, which is minus pi over 3. And then at that point, what is the cosine? Cosine is the x value, which is right here. So this is half. Okay, so this point right here, and then we have a point here. So x coordinate, y coordinate, yeah, this one is a special angle. This is actually half comma of minus quarter 3 over 2. And then the x coordinate is the cosine value. So cosine of minus 60 degrees or cosine of minus pi over 3 is minus quarter 3 over 2. Okay, by the way, your trigonometry should be strong enough so that you can evaluate these things without the use of a calculator. Okay? You're always busy trying to fill everything with a calculator, you'll be way behind. Okay? Your calculator, so you have to really know well. Even if you master everything, there is still a time which we cannot do without a calculator. When time will come. But for all the problems you see right here, you should not try to use any calculator. Okay? Although calculator is allowed.
Oh, okay.
So this right here is an
Does it have a
indeterminate
little,
form. This guy is an indeterminate form. Now when you plug it in, the value, basically we're plugging in, we're letting x up in. It's a question mark, we don't know. But it turns out to be this guy right here. And the work is over here. And do we have to show this work? Yeah, this work you have to show on the side. Unless you want to incorporate this work into this right here to do this. And then from there you can come this way. But you have to show me this work somewhere. Again, final answer is half. Any questions here? So that one was actually not a hard one. Now all the problems on this page, it should take about a minute. None of these problems take more than 1 minute on this page. So all the problems you see right here, everything up to problem number 12, from problem number 3 all the way to 12, it should take about a minute. None of them take more than 1 minute. That is, if you know what to do, all right? If you know what to do. So don't waste time. You have to be very, very careful with what you do. All right, okay, so I've did one problem. Is there any other problem which you want me to do? Either in this file or any other file? I think by this time, I did ask you to do so much more on your own. So I think at this time there should be quite a few problems. Okay, if you don't have any questions here, I think that itself is a problem. Okay, so it is not a good sign. So I don't know. Maybe you're not asking me, but you should have a lot of questions. Make sure that you can do all of these problems here. Okay, all the problems which I didn't do, they're all covered. Okay, one last time. Any questions on this page?
A question on number 8. How would you try to solve for theta in this case?
Okay, well, let's see. Okay, so let's look at it again. Limit, okay, number 8. So now we've come to number 8 here. So we have limit of sine square theta over theta. And as theta is approaching 0. So first of all, the limit theta is approaching 0, that's a good thing. Because when you plug in theta equals 0, what do you get? We get 0 over 0. So that's an indeterminate form. So we cannot get the limit that way. But note that the limit, the numerator is actually strong 0 because this guy's square. So in this case, the best thing to do is, how about if we split this? Note that the denominator is theta here. So in this case, what we need is, we have to use this theorem again. The only theorem and the only one and the only theorem we need is going to be this theorem. The same limit theta is approaching 0. Again, theta is approaching 0 or x approaching 0. You can use any letter you want. Okay, so the limit of sine theta over theta, and this guy is equal to 1. So basically, the first thing is you check for any limit, you check whether the limit is an indeterminate form, and then it is an indeterminate form. Then now, look at this limit here. The argument of the limit includes the trig function, sine theta. That's a trig. If you're dealing with a limit of an expression, including any trig function, cotangent, cosecant, doesn't matter, secant, sine, cosine, tangent, any one of the 6 trig functions, then that means we need to apply this formula, and this is the only one. This is the only one formula you need is up here. So this is a formula which you need 100% of the time. Virtually 100% of the time, you need this formula. And this is the only formula you need, basically. And of course, together with the other guy, which you can also use the other guy, theta over sine theta, the opposite guy, that's also 1 as well. Because that is just the reciprocal. So I use either this or this. But this one, same thing, because this guy right here, theta over sine theta, that's the same thing as what? The same thing as 1 over sine theta over theta. So really, I'm using the same guy. This is sine theta over theta. That's what that is. So if sine theta over theta is heading to 1, then 1 over that is, of course, going to 1 over 1 is the same as 1. So it's essentially the same formula. Okay, so now, in this case, what do we do? It's an indeterminate form, so we have to change the form. But note that we need to, we need to have this kind of form. But here we have sine squared. So in this case, actually, it's quite easy. What do we do? Don't think too hard. Theta is approaching 0. What do you do? The sine theta, let's write this as sine theta over sine theta. So this guy is sine theta. And then just write sine squared theta as sine squared sine theta times sine theta. Write it twice. Because why? Because in the denominator, you only have theta. That's what we have. So now, what we do is now let's group this guy together as a group. And then treat the sine theta separately. So now let's see. What happens? Now, can you apply the limit? Can you split the limit now? Can you say the limit of the product is the product of the limits? Take the limit of this and let's take the limit of that separately? Yes, we can. What is the limit of sine theta over theta as theta is equal to 0? But that will be 1. That's why the special theorem, the special formula. So we're not going to treat them separately, but we are going to treat this as a block, as a group. And that guy is approaching 1. Then times what is happening to sine theta? Oh, that's easy. Sine 0, which is 0. So we end up getting what? 1 times 0, which is equal to 0. When you actually look at it, it's really not so hard. And all the other problems on this page, you know what? They're not that hard. Well, I don't want to take it too hard, but they are as hard as these. Okay? I know when I say something is easy or something is not hard, all students always get mad at me, right? But you know what? I mean, but if you are well prepared and if you know what's going on, all of these problems can be done within 1 minute. Literally 1 minute. None of these problems really take any more than 1 minute. Okay? So they should be fairly simple. That means you have to study until you can do these kind of problems in 1 minute. Okay? That's what it is. So there are a lot of things you have to study. You know, you don't have to do every one of these problems here, but you must be able to do all of these problems, all right? So like when I look at these, yeah, I can do these, but I don't know the answer. I don't know the answer, but I look at this, but yes, but I can do it, okay? So that's where you stand. So you don't have to do every one of these, but you must get the hang of it so that you will be able to do these kind of problems. Again, no matter how many problems you do on the test, you'll always get something else. The same similar kind. The similar kind might be a little more complicated, but similar principles. So the rules are very strict. Don't do any of these hand-waving things. I want all your calculations to be very precise. Don't apply any kind of rules which are not sure. You have to be very, very clear on your calculation. And if you clearly do that, that's how it is. I mean, number 7, that was this one, this long, and number 8 was only this long. That's it. I did not skip any steps here. See, this is it. It's really not that long. Okay? All right, self clear. If you look at the other file, you get the same thing. So now what I'm going to do is I'm going to put all the burden on you. So limit trick 2, limit trick 1, all of these here. Make sure that you can do them, okay? So now let's be now over section 2.45 one more time. And we have done all this. But yeah, example 1, we have a lot of these files as well. Okay, so we have this. By the way, first, the derivative of the trig function. The derivative of sine is what? Cosine. And the derivative of cosine is minus sine. Okay? And the proof is on the other file. And then what I did tell you is you have to know these guys right here. The theorem, other 4 functions. They're good to memorize if you like. Okay? But all of these formulas here, they're only 1 minute away from the other 2 formulas. So let me write this down. Annotate here. And then this one, yes, number 0. The derivative of tangent theta is secant square theta. Of course, we may use the letter x. If you put the letter a, it's d dx. Take the derivative of tangent x with respect to x. So if we take the derivative of tangent x with respect to x, and that is equal to what? Secant square x. So many times this is actually used. Many times the variable is actually x. So the formula is going to look like this. So the derivative of tangent x is secant square x. And then the derivative of secant x is secant x tangent x. And the derivative of secant x, cosecant x is minus cosecant x cotangent x. And then so on. Here I use the letter theta, but the letter when you have these kind of functions here, the way you see is that you have a theta here, and you have a theta here, and you have a theta here. So how do you look at this? All it means that these guys must be a match. Is that clear? When you see these kind of things here, it must be a match. Theta, theta, theta. What that means is it doesn't have to be theta. It could be x, it could be y, it could be a, if you like. It could be 2x, it could be 3x, it could be x squared. These theta can be anything. As long as they match, the formula will be applied. Same thing with the limit theorem, which I already mentioned here too. The limit, and then we have covered the formula, limit of sine x over x over x over x, and then this is equal to 1 as limit is approaching what? Excuse me.
Bless you.
Having any? Okay, thank you. So yes, this is limit is 1, and this one approaching as x approaching
Putting it in my car
1.
and taking it
Sorry,
home.
as x approaching 0. If x
It's a lab kit.
if x is approaching limit, this limit actually becomes 0. But this is 1. So when you see this kind of a theorem here, I want you to understand exactly what this guy means. You see x right here, and you see x right here, and this x right here. So when you see this kind of theorem here, you have to understand that it's not really x. We are not interested in x here. So when you use this letter x here, what does that mean? Well, mathematically, what it means is that these three guys must match exactly. It does not mean that if you have 0 over 0, it's 1. It's not that. It's like this guy here. If you look at example 1, yeah, 0 over 0. So is that 1? No, that's not 1. It's not 1. So you have to understand what these statements, these mathematical statements mean. It's like this. When I say x squared minus 2x is equal to 0, let me ask you this. Is this problem the same as w squared minus 2w is equal to 0? Are they the same problem or not the same problem? Is this problem on w, is that the same as this problem right here? What do you think? Are they the same problem? Yes. In this case, if you let x is equal to w, then they're exactly the same problem. So whether I give you the problem in this form using the letter w, or whether I give you the problem in x, essentially they are the same problem. Is that clear? So the meaning is, when you see this kind of question and you see x here and x there, what does it exactly mean? All it means that this x and that x, they must match. They must match. They must be exactly the same guy. If I give you a problem like this, how about let's say x minus 2, x minus let's say 3 square, and then what? And then minus, and then 2 times w minus 2 times x minus 3 is equal to 0. Now, is that equation also similar to this guy too? Yeah. Essentially, they are the same problem. Whether I give you this, whether I give you this, they are essentially the same problem. Here, the question is, it's not about x. It's not about x. When you see these x's here, what it's saying is that this x and that x must be the same guy. That's what it means. These two guys, they must be the same guy. Exactly the same guy. Not roughly the same guy. They better be exactly the same guy. And if they're the same guy, essentially it is the same problem. So that's what it means. So you have to know how to read it. Therefore, if I write the formula this way, using the letter x, that is exactly the same as this guy right here. Now, when you get to section 2.6, you know what? Some of you may ask, are you ever going to see a problem where we have to do like this, tangent of let's say x, and then we have to take the derivative of let's say not instead of x, but how about in terms of y? So the question is, are we ever going to see this guy where we have to take the derivative of tangent x with respect to y? Are we ever going to see this? And then how about tangent of y? And then we take the derivative of this guy with respect to x. The question is, are we ever going to see a problem like this? Do you think we are ever going to see these guys? What do you think? Will we ever see these kind of problems here? Yes, we will. This guy is the topic of section 2.6. It is going to show up. So matching of this x and x, or theta and theta, is critical. If they don't match, then it will have an extra complication. But we just need one more step, that's all really. It's not that much more, but they're different. It is a different problem. So the question is, are they matching or are they not matching? Okay, that's the question here. If it's not matching, it is not the same problem. That you cannot apply the rule. So you have to know what these rules are. So just want to let you know that this guy right here, this is not secant square x, and this is not secant square y either. So this guy right here, the answer to this guy is not secant square x, and this is not secant square y. It's not secant square x, it is not secant square y. This guy here, same thing. This guy here is not secant square x, it is not secant square y. But if you have this, that is secant square x. And if you have this, that is good. If you have this right here, theta and theta matching, then that is secant square theta. So the question is, the thing is, when you see the theta here, we are not really interested in theta. And this is theta again, and there's the theta again. This is a triple match. So if you want to apply this formula, what do we need? We need a triple match. Theta, theta, theta. They must match exactly. So instead of theta, we can have x, we can have 2x, we can have x squared, we can have x squared plus 3. The theta can be any function. Any function in any variable. In fact, the theta can also be x plus y. It might sound very weird to you, but you are going to see things like this. Here, so here, then x plus y. And then what? Of what? This is the derivative of what? Derivative of tangent of x plus y. So the derivative of what? Tangent of x plus y. So let me write it. So this one here, tangent of, this is tangent of x plus y. What? Do you think you can tell me what this is? Can you tell me what this is right here? Who can tell me what this guy is? What is the derivative of tangent of x plus y with respect to x plus y? Do you think what this is? Now, in order to do this problem right here, in order to do this problem, do you think we can apply this theorem right here? Can you apply this theorem right here? Can we apply this theorem right here? Can you apply this problem? Can you apply this theorem right here to do this problem? To do this problem right here? Yes or no?
Yes.
Yes, we can. And that will be what? That will be secant square of x plus y. Now here, class, if I give you, how about this? How about, let's say, let me do this here in a black, and then I'm going to click here. Let's say we have a problem like this, and we have a problem like this. Now, which problem looks easier to you? This number 1 or number 2? If I give you two problems like this, which problem looks easier to you? Does number 1 look easier to you, or does number 2 look easier to you? What looks easier to you? Which problem looks easier to you, number 1 or number 2? Now, number 2 problem does look more complicated, and number 1 looks easier to you, to many of you. And many of you might think, oh, number 1, isn't that the easier one? Because it kind of looks easier. No, not really. Number 2 is covered by section 2.4. This is section 2.4. This is right now what we're studying right now. But number 1, this guy will be covered in section 2.6. So even though number 2 looks more complicated, actually number 1 is more difficult. It involves more steps. One more step. Doesn't really take that much steps, but we will cover this in section 2.5 and 2.6. The 2.5 and 2.6 is roughly like one section, one topic, but 2 parts. So section 2.5 is one part of the chain rule, and section 2.6 is like the second part of the chain rule. We actually call it by a different name. We call it implicit differentiation, but hopefully we'll get there today. So what I'm trying to say is, number 1 and number 2, number 2 is x plus y here, and x plus y here. So this guy looks like this. Looks like d dx of what? d dx of tangent x. That's what it looks like. So number 2 is essentially the same as this guy here. Oh, that is the derivative of tangent x with respect to x. Basically this guy. But number 1 is different. This is y and x. They're not matching here. So I want you to be very, very careful when you look at these theorems and formulas and problems. I want you to be very, very careful. Again, you know what? This term right here and this term right here, they're essentially the same thing. Because all we're saying that this x and this x is matching. However, if I take a form like this, w squared and then what, minus 2x is equal to 0, is that the same as the other problems? No. If you see a letter x here and a w here, now this is a different ballgame. This x is not the same as w. This is now a different equation. You got there? So when you see the letter x, you have to understand this x means that all the x are the same. It's like saying, like I said, you have already seen this before. If f of x, if you write f of x is equal to, how about this? Let me write this again. If you write, that's the f of x. What is f of x? Let's say f of x is equal to the f of x is equal to, let's say, how about let's 2x and the plus 1. If you let's say f of x equals 2x plus 1, all we are saying is that this x right here is the same as this guy right here. It doesn't matter whether you use the letter w or whether you use the letter L. Whether you put x squared here, you can put any x, anything here. All we are saying is that this guy here, this guy right here, it's exactly the same as this guy here. We are showing that these x's must match. X's must match. They must be exactly the same guy. Exactly. That's what we're showing. There's no secret about x here. Okay? When you write x here, that means these x's must match. That's what it really means. Okay? There's no secret to x. We can use w, we can use k, we can use y, we can use anything. We can use any letter we want. Okay? So make sure that you understand these. Okay, so now let me go back here. We have these 4 formulas here. Maybe I can prove one. Did any of you want me to prove one, or if you do, okay. Make sure that you can, you know all these formulas here. Again, in order to prove these formulas, what do you need? You need 2 things. You will need the derivative of sine and the cosine formula. The derivative of sine x is cosine x, and the cosine x is sine x. You need that, and you need the quotient to prove any one of these here. Every one of these, that's what you need. Okay, so any of you want me to show you prove any of these theorems here? No? Yes? Did I do one or no?
Yes.
Yes,
you did.
Pick one. Pick one. Which one looks the most scariest to you? Or do they look all the same? So like I said, the ddx of what is that
Do
you
the
need?
cosecant x.
So what is it? Which one?
I said you do the cosecant x, or cosecant theta one.
Okay. Now let me tell you the ingredients of things you need. So in order to prove this, what you need, this is what you need. ddx of sine theta. ddx of sine, let's just use theta here because we have theta. So dd theta of sine theta. dd theta of sine theta is equal to what? ddx of sine theta is equal to what? Is equal to cosine theta. And the dd theta of cosine theta is sine minus sine theta. You have to know those. And then plus, you have to know in this case, you have to know the quotient. So f over g prime. So what is f over g prime? This is equal to quotient. Every one of you, do you remember this guy? The quotient is this guy right here. So this is equal to g squared. And then g squared, and then what? This is f prime g. And then minus f times g. F prime g minus f g prime. That's the quotient. That's the only need. And in this case, actually, I should have maybe I should have written this, but anyway, I could have written this way. So sine of x. So I can write sine of x, the derivative of sine of x. So I can write prime here, and we can write this as what is equal to cosine x. That's the same as this right here. Okay. Okay. So now let's look at this. Okay. So proof. So we have to start from the left hand side. So let's start from dd theta of cosecant theta. d theta of cosecant theta. Oops, you know what? I think I should change it to a thinner form. Cosecant theta. Okay, so now what is the cosecant theta? Now the question is, do you know anything about cosecant theta? Well, not much. But when it comes to these other functions, you have to know its definitions. Excuse me. So all of these four functions here, secant, tangent, secant, and cotangent. Basically, if you don't know any of these rules here, then what? You have to just convert them into sine and cosine. Basically, that's one of the rules. So all of you have to know the definition of cosecant theta. The definition of cosecant theta is 1 over sine theta. So you convert that. So the definition of cosecant theta is sine theta. So therefore, we get is 1 over sine theta. So cosecant theta is now equal to 1 over sine theta. So we now have 1 over sine theta. So now what? Now this is the derivative of the quotient. We know that the derivative of 1. We also know the derivative of sine theta. So if you have a quotient like this, and you do know the derivative of the numerator and the denominator separately. Again, if you know f prime and you know g prime separately, and this is what it is, we know the derivative of 1, which is 0, and we know the derivative of sine theta, which is cosine theta. That is with respect to theta. So in this case, what is that? We apply quotient rule. The quotient rule is going to be now the g squared, so that will be sine theta squared, which is sine squared theta. So sine squared theta. And then this, now over the denominator, f prime g. What's f prime? Well, f prime is actually 0. You know what? Let me write 1. Let me just write 1 here. Let me show you the middle part. The derivative of sine is 1. Derivative of 1 and times what? G is cosine theta. So we get this, sine theta, and then minus f. F is just 1 times g prime. What is g prime? That will be cosine theta. So we get this. Now, what is the derivative of 1? What is this one?
0.
That's 0. So that term, yeah, this is times here. So the entire first term goes away. And so that leaves this. What is that? That becomes minus. And so let me put a minus in front of it, and then this here. And then let me write, let me see, cosecant. Okay, I'm going to write sine theta. I'm going to write this as sine theta times sine theta in the denominator. Times sine theta. Let me just write sine theta like this. And then let me write cosine theta over here. Cosine theta. So I'm going to write like this. Why am I writing it this way? Because I want to get to the other side. So now what is it equal to? Minus. What is 1 over sine? 1 over sine is cosecant theta. So 1 over sine is cosecant theta. So that's cosecant theta right there. So 1 over sine is right there. 1 over sine. Basically 1 times this, if you like. So this guy is cosecant theta. And times what's this guy here? Well, this guy is cotangent theta. That's the definition of cotangent, by the way. The definition of cotangent is what? Is cosine over sine. So the definition of cotangent theta is cosine theta over sine theta. So this is it. All the other guys, they're very similar. So that's how we do it. So all of these guys, it takes about 1 minute. Of course, you need to know what you use. Always check your ingredients. What formulas are assumed? What are you allowed to use? In this case, you use this fact, and you use the product of quotient in this case. And all 4 of them, it's kind of like that. Okay. Okay, then any questions on this proof? Any question about any of these proofs here? So you have to know the definition of these trig functions. Tangent theta is sine theta over cosine theta, and so secant theta is 1 over cosine theta. Yeah, you have to know this, of course. Okay. Definitions of these trig functions. Okay, any questions here? No questions? Okay, save. Then I'm going to save this, and then now let me clear all this. And so let me just scroll this down, and then we have this. Now, what is this? Okay, so now full screen now, and now we have all this. What is example 3 and example 4? Example 4, example 5. Okay. After example 5, what formulas do you think we have to apply here? If you have to do example 5, What formula do you think we should have to apply? What's the leading rule? Example 5, what do you have to apply here?
You can.
How do you find the derivative of this guy? What is the rule we should apply? Yeah, what is it? Right? Is it right?
Sorry about that. I think you can apply the sine x over x.
Which one? This one is sine x over x.
Yes.
But the denominator is x squared. And by the way, do not get the. You know what? Do not get mixed up. Do not get limits, problems, and derivative problems. One of the problems students are having is this. The students are getting the derivatives and the limits mixed up. So do not get limit problems and derivative problems. Okay? Do not get confused between what? Between limit problems and derivative problems. Limit is not a derivative. They are obviously related. But limit form is a limit formula, and the derivative is a derivative formula. Okay? So again, derivatives and limits, sometimes I see people like this. I see people like this here. We have a limit here. So the limit of let's say sine x. Let's say sine x, and then plus what tangent x. Then at tangent x, and then over x. Then x approaching 0 here. And now sometimes when I give a formula like this, you know what sometimes students do? They apply quotient rule. But you know quotient rule? Well, you cannot apply that quotient rule on differentiation. This is a limit. So do not get the limit problems and the derivative problems mixed up. All right, is that clear? That's one thing you have to be careful. Now here we have to find the tangent line, and if you want to find the tangent line, we need to find the slope of the tangent line, which is actually derivative. So here, the first step is to find the derivative. Now note that finding the derivative is not the same as finding the limit. Is that clear? Limit problems and derivative problems are not the same. Ultimately, they are related somehow. So yes, they are. The derivative is ultimately the limit, but again, do not get the problems mixed up here. Do not get the problems confused. And if you just memorize formulas and you have no understanding, that's what you will do. So make sure that you understand the difference between derivatives and limits. Okay, now example 5 again. What's the first thing we have to do here? What rule do you think we should apply?
Is it quotient rule?
That's right, quotient rule. Now the question is, do you think we can apply the quotient rule? Not really, because the denominator is 1 squared now. 1 plus x squared. It's a binomial. So when you have a binomial denominator like this, then basically that means you cannot avoid quotient rule. So in this case, you have to apply the quotient rule and get f prime of x, and they get the tangent at this point, and they get the normal line. So I'm sure that you can do that on your own, and so why don't you do that on your own? Now what I'd like to do is look at let's look at example 4. Example 4 here, we have f of x plus sine x plus 1 over cosine x. And now we are asked to find the derivative. So it looks like this is a quotient. But note that the denominator is a single term. It's like a monomial. When you have like a monomial denominator, then what can you do? Then you might be able to avoid the quotient rule. Because the quotient rule, even though it's a nice rule, it is actually one of the ugliest rules out there. So this one, how about this? So the question is, are you going to apply quotient rule here? Quotient rule of differentiation, that is the quotient rule of derivative, or you should apply this, or how about if we split the fraction? If we split the fraction, we get this. If we split the fraction, f of x is equal to, we write this, f of x, we have a monomial denominator, this is sine x over tangent, sine x over cosine x, which is what? Which is tangent x. Yeah, this one is tangent x. And a plus, a 1 over cosine x, so that's going to be secant x. Oh, we can write like this. So do you think that we can actually find the derivative from here in this form? And if you write it this way, then we don't need quotient rule. We can just use the derivative of formula for tangent and secant. So in this case, let's see, what is the derivative here? I can do that because this is so simple now. This f prime of x is equal to what is the derivative of tangent x? So that is equal to secant of x, the plus the secant of, and the plus the secant x is secant x tangent x. Secant x, this is secant x, and then times tangent x. Times tangent x. So all I need to do is put a square there. That's it. Okay? So for this guy here, if you want to, you can apply quotient rule. But the denominator is like a cosine x. It's like a monomial, one term, and you can split the fraction. And when you do that, this is what you get. Oh, this is you get this right here. This is f of x. This is not f times x. This is f of x. And then when you see this, then you can say what? You can say, oh yes. Oh yes. So we are glad that you don't have to use quotient. You know what? I'm always very happy when we don't have to apply quotient. But sometimes quotient cannot be, sometimes you can avoid the quotient, and sometimes, many times you can. But wherever you can, then you should probably stick it. Okay? Because if you go by the other way, then generally it is more work and more complicated and more messy, and therefore higher chance of making mistakes. Okay? All right. Any questions here? Now, when you study this on your own, I do recommend you to do that problem in a different way. So here we just split the fraction and then apply the tangent and secant. But how about if you apply the quotient rule and see what happens? So when you study, applying a quotient rule to this guy is not bad. So I want you to look at all these different ways here, but I want you to understand what different ways are out there. So what's the way to learn the best way? If you want to learn the best way, there's only one way. You have to learn every way. So study every way. That's the only way you get to learn the best way. If you just learn the best way, then will you know the best way all the time? No. You will have a breakdown at some point. So the best way is to learn every way. And when you learn every way, then you will get to learn the best way. That's how you learn the best way. Okay? Because you don't know, when you have a problem, you don't know what the best way is. So try different ways. So try different ways. Oh, by the way, let me now, you know what, before I move on, let me just give you a hint. Let me give you a hint on today's quiz, problem number 1. On problem number 1, let me give you a hint. And problem number 1 is actually a limit problem. And if you look at the limit problem here, we have 0 over 0. What are the indeterminate forms? These are the indeterminate forms, right? The indeterminate forms are, these are the indeterminate forms. So let me just put commas here. Now, when you look at these indeterminate forms, what do you see? All the indeterminate forms you see in this class, they all involve 0 and infinity. You see that? You have a 0 there. You have what we see here. You see a 0 here. You see a 0 here. You see a 0 here. You see all the zeros and 0, and then you see these infinities. Do you see anything else? Do you see anything other than infinity and 0? No, you only see infinity or 0, right? Don't you? So when it comes to indeterminate forms, you have to work on the zeros and the infinity. Something is not 0 and something is not infinity, then don't bother. Okay? Watch out. So I'm talking about example 1. Example 1 should take about somewhere between 5 to 10 minutes. It should take about half a page. It should maybe take about 10. You know what? 10 minutes is way too much. Somewhere between 5 to 10 minutes. If you're prepared well enough, then about 5 minutes. But do not convert this 5 minute into a 30-minute problem, as some of you will do. Some of those people who are not here today, they might, and if you take the quiz, they might convert that 5-minute problem into a 30-minute problem. and the plus, they'll probably make mistakes because it will be now too messy. So you have to be very, very careful. So these kind of problems here, you have to watch and look at it carefully and scan it, and you have to see what exactly needs to be done. Don't do anything unnecessary. When you start doing things unnecessary, then that's when you start messing up. Is that clear? So be careful here, all right? So that's that. And I think we have spent enough time on section 2.5. It is now time that we move on to what? Move on to section 2.5. Okay, so is this the end of section 2.4? Yes, it is. This is the end of section 2.4.